Welcome back again. Yesterday we were discussing the solution to the question paper of 2020-21. It has come in, I think, December in 2020. Uh, so first question we have discussed, and there are 5 more questions. And of course, in question paper you will be given 6 questions in total, and you have to answer any 4 questions. So you have a choice, enough number of choice. So the second question, it says that if A is any element having order 3, and if this holds, that is if this holds, that is order of A is 3, then we have to prove that a centralizer of A is equals to centralizer of A square. I think we didn't attempt this question yesterday. Yeah. Hello. Was it done?
Yes, sir.
Uh, did we prove yesterday this theorem, this result? I don't remember. Or we attempted only question number 1, I think. And give an example to show that conclusion fails if order of A is 4. And then we need to find the order of each element of U14. And then we need to find whether it is cyclic or not. If it is cyclic, then we need to find all generators. So let us try to solve this. So we have been given that there is some group and an element which belongs to that group having order 3. So let us consider, let G be a group and A belongs to G such that order of A is equals to 3. Fine. Then we need to prove centralizer of A is equals to centralizer of A square. And you know that the definition of a centralizer of an element of a group is the collection of all those elements of that particular group G such that XA equals to AX. So it is the collection of all those elements which commute with every element of uh, with every other element of group G. Okay, so this is the definition of centralizer of particular. Actually, centralizer is in one sense is a local property or the element based property. So we find a centralizer of an element of a group, not of a group. Okay, just like we used to talk about center of a group. So that is for that property is defined for a group, and this property is defined for a particular element. Okay, so okay, let us see how we can prove. Before proving this, we need to see. Just a minute. We need to see that. Let us note. You can write it in maybe in solution, or you may directly write down that this holds. Okay, and the one I'm going to write in blue. So if x commutes with A, that is x equals to AX equals to A XA, then a to the x to x e to the power n equals to e to the power n x, where n belongs to the set of natural number. Okay. So this is one thing we will be using. Okay. So for this we can use Untitled. Let it means that we are talking about centralizer of A. So let some element, for example, let x belongs to centralizer of A, that is A commutes, x commute with A. Okay. So x is any element from CA. So this then we have xa equals to or ax equals to whatever you feel like you can write. Let us write ax equals to xa. All right, because x belongs to the centralizer of A. Fine. So it means that this is true for n equals to 1. Thus, suppose this is star. Star is true for n equals to 1. Now assume that star is true for n equals to k, where is k is some natural number. Okay, then what we have? We have x e to the power k equals to e to the power k x. Fine. All right. Now consider. Okay. So now consider, because we have assumed this, we are using mathematical induction. So we are considering x a to the power k equals to a to the power k times x. And this implies that x then we need to prove that x a to the power k plus 1 is equals to a to the power k plus 1 times x. Okay, so this is what we need to prove. So for this, we can multiply on both sides. Let us write it x a to the power k, and in the left side we can multiply with the xa, and here also we can multiply with xa. So a to the power k and x. Okay. So, but we know that x belongs to C of A, that is ax equals to xa. So we can write here x and then x square, that is x square and a to the power k plus 1. And this is equals to here x and a to the power k plus 1 times x. So if we use left cancellation law here, so we have x a to the power k plus 1. This is equals to a to the power k plus 1 times x. So we assumed that this is true for n equals to k, and we came to know that this is also true for n equals to k plus 1. And therefore, by mathematical induction, so by principle of mathematical induction, we have x a to the power n equals to a to the power n times x, where n belongs to the set of natural number. Okay. So these things, what I have written in blue color, these are optional for the sake of your better understanding. I have written this part. Okay. So maybe in exam you may be having some question related with this, so that you can solve using this. Okay. So now what we have, we need to prove this until we have not started. Okay. So let us see the main proof. So let us assume that let some element x belongs to the centralizer of A. Then x also belongs to centralizer of, because if x commute with A, then it is also going to commute with a to the power n. where n belongs to the set of natural number, just we proved. Okay, and in particular x belongs to C of a square. Fine, x belongs to centralizer of a square. Fine. So we assumed that x belongs to centralizer of a, and this also belongs to centralizer of a square. And this implies that centralizer of a is contained in centralizer of a square. All right. And moreover, until now we have not used this. Okay, order of a is 3. Fine. So one more thing, in general, you can say here that centralizer of A is contained in centralizer of A to the power n. Fine. So you may be asked to prove this. Fine. So that's why I told you that you may know, you should know the general proof for this. But in particular, sorry, our proof is starting from here. So we have this, and let us assume that this is the equation number 1, or this is inclusion number 1. Okay. Now since order of is 3, it follows that a to the power 3 equals to identity, and this implies that a to the power 4 equals to a. All right, a to the power 4 equals to a. But what we know that centralizer of A contained in centralizer of A square, just we proved by 1. We have this, and this implies that if we replace A by A square, so this would also hold. So centralizer of A square will be contained in centralizer of A square or sky square. Fine. That is centralizer of A square is contained in centralizer of A to the power 4. And this implies that a centralizer of A square is contained in A to the power 4 is nothing but A. Centralizer of A. Fine. So this is number 2. So from 1 and 2, we get the desired result. Okay. In 1 we have proved that centralizer of A is contained in centralizer of A square, and here we come to know that the centralizer of A square is contained in centralizer of A. And note that this holds. For this we are using that is order of A is 3. All right. So next, so from 1 and 2, we conclude that centralizer of A equals to centralizer of A square. So this completes the proof of one part. And let us see what is there. So they are asking that give an example, to show that the conclusion fails if order of A is 4. So last time we have seen so many students written some proof in a similar way, just like we are using here. Okay, but because they wanted some example, so we need to give some example. Okay, in counter of this inclusion. So for this, let us assume consider the group D4. Consider the group D4, and in D4 we have the identity that is R0 and R90, R180, R270, horizontal, vertical, and then we have diagonal and another diagonal. So these are the elements in D4. Okay, so let us take R90. So here R90 has the order 4. Okay, R90 has order 4, and then centralizer of R90 is are those elements of D4 which commute with that particular element. Centralizer of this is equals to E, that is R0, R90, R180, and R270. So this is going to be centralizer of R0, and let us uh, okay. Okay, so this is the centralizer of R0. Now we need to find the centralizer of R0 square. Centralizer of R90 square. So R90 square, that is centralizer of R. 90 square means what? 90 square means R180. R180. And this contains those elements of D4 which commute with this. Okay, and if we find that the elements which commutes with R180 are all elements of D4, that is, it is equals to D4, and this is not equals to this is not equal to R centralizer of R90. So this is an example where we find that if order of A, that is some particular element, becomes 4, then the above conclusion, that this conclusion may not hold. Okay, and let us. I think there are some more part. Okay, find the order of each elements of U14, and so that this it is cyclic, and find its all generators. So I think you can do this. Hello. U14, anyone who can tell me the elements of U14? Hello, quick. Quick reply.
1, 3,
1, 3,
5,
5,
7,
7, really?
9,
11,
9,
11, 30.
30. So the order of U14 is 6. Order of U14 is 6. Order of U14 is 6. So question is that whether it is cyclic or not cyclic. And first of all, we need to find order of each elements of this U14. And when it becomes cyclic, when A14 becomes cyclic, when a group becomes cyclic. Anyone?
when order of any element is equal to the order of group.
Very good. Please note down 1 point for this. So if we can find at least one element in this U14 which has order 6, all right, then that element will become a generator of U14, and hence U14 will be a cyclic group. Okay. So let us write here element order. First, let us complete this. 1, order is 1. Order of 3. Order of 3. कितना होगा? You can note it down. It is 6. Okay. Order of 3 is 6, and 3 into 5 equals to 15, and 15 divided by 14. So it will leave remainder 1 and divided by 14. So order of 5 is going to be 6. Again, because 5 and 3 are inverse of each other. And then a 9 and 11. If you see 9 and 11, so 9 into 11 we have 99. All right. And when you divide it by 14, then 14 7s are 98. Okay, so their order is also going to be same. Okay, so we need to find the order of 9 and 11. So what is not order of 9 and 11?
Mm.
Hello.
3.
3. 9. 9. Okay, 91. 3. Okay, yes, it's 3. 3. Both have order 3. Okay, and then here we got pairs. They are inverse of each other. They are inverse of each other. So 13 should be self-inverse. So order of this should be 2. So we have element. We have order of each elements of the group U14, and we got there are two elements, 3 and 5, which are having order 6. Okay. So you can write note that a group is cyclic if there is an element. A group G is cyclic if there is an element A such that order of A equals to order of G. That's all right. Okay. So there should be at least one element which order is equals to the order of group. So here in this particular case, here we have order of 3 is equals to order of 5 equals to 6. Fine. So U14 is cyclic and U14 is generated by 3 and 5 as well. And if you want more clarification, you can use like this: 3 to the power 1 equals to 3, 3 to the power 2 equals to 9, 3 to the power 3 equals to 27. 27 when you are dividing it by 14, you are going to get 13, I think. Huh? Yes. Okay. Yeah. And then 3 to the power 4. This is equals to, you just square this one, both side. So 3 to the power 4, it means 81. We are going to get 81. And 81 divided by 14. What you are going to get? 81 divided by 14. Remainder. Hello.
11.
11. Okay. And 3 to the power 5. Of course, 3 to the power 6 is going to be 1. You
5.
know. Yeah, 5 is remaining. So like this. So it means that 3 is generating U14. You can show something like this. Similarly for 5 also. Is it okay? So we can move further on next question. If you have any doubt, you can ask. Okay, so let us see next question. Question number 3. They want the definition of center of G of a group, and prove that center of S4 is identity. It contains only identity. So this time you may have question like this, that the center of Sn is identity. It may be in general, okay? So that you need to be prepared. Fine. In general form, they can ask them in this question in general form. So I think you can define the center of G. center of G. So let G be a group. Then the center of G is denoted and defined by this is equals to all those elements of G such that hello what you will write here, Ax equals to XA for all A belongs to G. Fine. So this is the definition of center. Now next part we need to prove that the center of S4 is identity. Okay. So next part, let us see. In case of, or you can write since E is the identity of S4, so clearly E belongs to the center of S4. Center of S4. So E belongs to center of S4 because identity commute by definition with every elements of the group. So we need to prove what? That there is no other element other than identity in hello, are you getting my voice? Hello.
Yes, sir.
Okay. So we need to take another element in ZS4, and we need to prove that that element cannot be other than identity element. Okay. So this is a way where we can prove, or that cannot belongs to ZS4. So for this, let us assume let sigma, which is not equals to identity, belongs to ZS4. This is a ZS4. This is another element of we are taking from the center of S4. Okay. Because S4 is a group of permutation, which is created with the help of, or which is constructed with the help of 4 symbols. Suppose, for example, they are 1, 2, 3, and 4. Okay. So this implies that there exists X belongs to the set 1, 2, 3, and 4, such that sigma X is not equals to there exists sigma X which is not equals to X. Okay, for some. Okay, no need because I've written there exist. You know why? Because sigma is not identity. In identity, what we have when we define identity permutation, 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4, like this. Then we used to write this identity. Okay. So there should be some element in this set 1, 2, 3, 4 in which there is some element X, for example, which is not mapped to self. Maybe we may be having 1 goes to 1, 2 goes to 2. Okay, 1 goes to 1, 2 goes to 2, and 3 goes to 4, 4 goes to 3, something like this. There is a possibility that two elements may be mapped to onto self, but other two are mapping onto other elements. Okay, So that's what we are writing here. Are you getting what I'm trying to explain? Hello. Okay. So let us take another. Okay. So we have taken this sigma such that sigma is x is not equals to x. Now let sigma of x equals to y, and of course because sigma of x is not equals to x, so y cannot be equals to x. And let us consider another element from Z, from this set 1, 2, 3, and 4, such that such that um, such that mm, such that Z is not equals to x, and Z is also not equals to y. Okay, so we are considering other element which is different from x and y, which is different from x and y, and there is a permutation we are taking of y and z, these two elements. Okay, we are taking a permutation, other permutation y and z. It contains y and z. So now we will prove that this sigma will not commute with tau, this tau. Okay, so sigma and tau, when they are operated on x, so we are going to get sigma and tau x. So tau x, so sigma tau x is because here x is not there, it means x will be fixed. So we have sigma of x and sigma of x equals to y from here. Sigma of x equals to y. Again, let us consider tau and sigma, and when we are, let us compute the image of x under this map. So tau of sigma of x. So sigma of x is equals to here y. You see, sigma of x equals to y, and tau of y equals to z, because we have considered this. Okay. So we have a y and z. From these two, what we have? We have sigma and tau is not equals to tau of sigma. So it means that there exists a permutation yz which does not commute with sigma. So therefore, this implies that sigma, or we can say that this is a contradiction, not commute, which is a contradiction. Contradiction. So this implies that sigma does not belongs to ZS4. So any permutation which is other than identity permutation cannot be a member of center of S4. Okay. Let us see next part. So for n greater than 2, we need to prove that every even permutation in Sn is a product of 3 cycles. Every even permutation is a product of 3 cycles. So let us see the proof. For n greater than 2, what we need to prove that every even permutation is a product of three cycles. Okay. So let this is the question. Okay. So let sigma belongs to Sn be an even permutation. be an even permutation. Be an even permutation. And you know the definition of even permutation. What is the definition of even permutation? Definition of even permutation is that if it can be written as a product of even number of transposition. So this implies that sigma can be, or sigma is a product of even number of transpositions. All right. So it means what? Sigma is a even product of even number of transpositions. Even number of transpositions. It means that product of even number of transposition can be written as product of 3 cycles we need to prove. Thus, we need to prove that product of even number of, we need to prove product of any pair of transposition is a product of three cycles. Okay, so let us assume. So consider transpositions. Consider true transpositions and C. So there are 3 cases we can consider here. A, B, or you can write without comma. There is no problem. AB equals to CD. AB equals to CD. Then AB and CD. This is equals to AB square. And because transpositions are self-inverse, this is equals to identity. Okay, so we can write it as a 1, 2, 3, and 3, 2, 1 like this. So there are 1, 2, 3 are some symbol, but identity permutation we can write like this. So this becomes the product of 2, 3 cycles. All right, identity also becomes product of 2, 3 cycles. Let us consider the case AB is not equals to CD. AB is not equals to CD, and AB this set and this set CD is intersection of these two set is non-empty. Non-empty means that is there is something common in these two. It means maybe one may be equals to another one. Thing is that, okay. If it is non-empty, it means that but and also this is not equal. It means that B or C may be different, A or D may be different. There may be something different, okay. But something may be common also, because this is non-empty, okay. Because this is non-empty, okay. They are distinct. So distinct may be one sense that A, B, C, D, everything is distinct. So in that case, it becomes empty. But here also considering that this is non-empty, it means there is must be something is common. Either B may be equals to C or A may be equals to D, something like this. Okay. So let B equals to C. Say, okay. So AB this transposition, and let us take product with CD. So we have A, B, and then in place of C, we can write B. So we can write B, D, and after multiplication, we can have A, B, D. So this is also three cycle. This is also three cycle, product of three cycle. Let us consider third case. Third case is that we are considering that AB, and intersection CD. This is equals to 5. That is, there is nothing common. And of course, if there is nothing common, so A, B, and okay, there is nothing common. Okay, so of course they cannot be equal then, right? So let us write A, B, and CD. A, B, and CD are the product of these two. So when we take product of these two, we can write A, B, and in between we can insert B.Sc, and because the transpositions are self-inverse, so we can write here CD. Okay, so these two are nothing but identity together. Okay, so let us club the two transposition AB and BC in one, and BC and CD in other. Okay, so AB and BC, when we multiply these two, we get ABC, and when we multiply these, we get BC and D. So this is also product of three cycles. Product of three cycles. So there is no more case which is left here. Next, there is another part. So they have given that sigma is some permutation, and then they want to express sigma to the power 17 as a cycle. Okay, so let us see. So given that sigma equals to 157 25316, and you see that 5 is common in first and second, one is common, one is here and one is here, so they are not a product of disjoint cycle. So you can first write them as a product of disjoint cycle, and for this when you compute, you will be getting 165 and 327 like this. So this is a cycle of length 6. So order of sigma will be equals to what? Hello. Order of sigma. Anyone? What is the length of this cycle? 6. So order of sigma is going to be 6. So this implies that sigma to the power 6 equals to the identity. And now they want sigma to the power 17. So sigma to the power 17, we can write sigma to the power 18 minus 1, like sigma to the power 18 times sigma to the power minus 1. So sigma to the power 18 is nothing but we can write sigma to the power 6 to the power 3, and sigma to the power minus 1. This is nothing but identity. So we have a sigma inverse. Okay, and the sigma inverse, we have sigma this one, and so therefore we can write sigma inverse 7 2. You can write from here in reverse order: 7 2 3 5 6 and 1 like this. So this is equals to sigma to the power 70, right? So this completes the solution of this question. Okay, so I think we don't have time now. So rest question we will be discussing in tomorrow's class.
Thank you for watching this video. To stay updated, please subscribe to our YouTube channel, Cosmos Learning. Happy learning through Cosmos Learning. To watch more, click on any of these cards. Thank you once again.